Hi, this is Jim Plank, and this is the next video in the network conversion paper, and this is a video going over the first case study in the paper. Now, in the previous videos, we've gone through 7 networks that do 15 conversions between values, times, and spike trains. What we do now is use one of those to build a very useful network for processing output. Now, um, before going through that, let me just do my standard spiel. If you've come upon this without reading any of the previous material, go to the main repo for all of this work, which is up there in that URL, and either read this README or watch this main video here, which tells you all about what these networks are doing, what the neuroprocessor is, how to download and run the open source software, etc. Once you do that, you'll be able to go through the material in this video much more easily. Okay, I am in the repo for that open source software. I've pulled it here onto my Macintosh, and what we're going to do is go over the network in figure 14 of the paper, which is here in figure 14. Okay, now what this network does is it's a very useful network. In many neuromorphic applications, you train a neural network so that you count its output spikes to determine what's going on. For example, in the asteroids video that you saw in the initial video, there are 2 output neurons for whether or not to fire. There was a fire and a not fire neuron. And at each simulation time step, we'd run the neural network, and then we count the number of spikes on those 2 outputs and compare them, and whichever one's greater determines what we do. If the fire one has more spikes, then we fire. If the don't fire one has more spikes than we don't fire, and ties are broken in favor of one or the other. Not sure what it is in that one, but that's how it works. Now, a lot of neural networks are trained in this way because it's a very effective way of doing output processing with the spiking neural network. The problem with it is that having a host read output spikes is inefficient from a communication standpoint. Again, our neural network can run on the order of 200 megahertz, mega times steps a second. Communication often chunks along a lot slower. On our FPGAs, communication's around 10K per second. So big factor slower. So it's a good idea to not have to communicate a lot of output spikes to make the host compare. What this neural network does is it does the comparison. So it assumes that there are a bunch of output spikes on this Y train and on this N train. Those are our 2 output neurons. Right? And then this neural network ends up basically counting and comparing the spikes and turning them into a single spike. If there were more spikes on the Y neuron, then this neuron will spike exactly once. If there are more spikes on the N neuron, this neuron will spike exactly once. If there's a tie, ties go in favor of the Y. If there's a tie, then that's the neuron that will spike. Okay? So it's taking a effective way of training a neural network by doing this counting and comparison, but converting it into something that is very communication efficient when you do a real embedded installation. Okay? Now, the way this neural network works is kind of a composition of the other neural networks, or actually some other neural networks in other papers as well. Basically, this little subnetwork converts these trains to times. Okay, actually to times here, so that the number of spikes here ends up being communicated here as a time. Then this little subnetwork here compares those times, and if the A time is shorter than the B time, the A neuron spikes. If the B time is shorter than the B neuron spikes. So basically it's converting the train to its complement time, comparing the times. So that works great. Unfortunately, when they fire together, if these two have both fire an equal number of times, then these two neurons fire together and the output's a little messed up. And so what this network does here is it cleans up the ties. And in fact, it's a binary AND network that comes from a different paper that we wrote. So it's basically doing a binary AND that says if both these fire, then we do this C neuron's going to fire and we're going to break the tie in favor of yes. If they both don't fire and only one of them fires, then that's cool. Either the D or the E neuron will fire, and that means either the Y or the N neuron will fire. Okay, so again, very useful taking two spike trains, comparing them, and then emitting a single spike to say which one spiked the most. Okay, so we have a shell script to create one of these networks and then exemplify it. That is going to be in shell script number 9, spike counts. Okay, when we run it, it's going to take a maximum number of spikes. Let's just use our standard example of 8. The number of spikes that come on the Y neuron and the number of spikes that come on the N neuron. So let's do 3 Ys and 2 Ns, and then the framework. We run it. Of course, we got a ton of neurons here, so we're going to have to make this window very big. But the bottom line of what we should see is since there were more Ys than Ns, this Y neuron should spike and this one should not. And as we see, it does, and that one doesn't. Now, I could go through the mechanics, but it's not really that illustrative. Again, the early part of this is a conversion of a spike train to its complement, or to its complement time. These compare the times. This one is an AND network that cleans up the ties. And that's what you'll see. Since there wasn't a tie, you'll see the C neuron didn't fire. Okay, let's go ahead and swap the Y and the N. So now there are more N's than Y's. And what you'll see is, yeah, the N neuron fires, but the Y neuron doesn't. The timing doesn't matter. It's going to fire at some point, and the timing is not specific to anything. If we really wanted it to spike at a certain time, we could put an extra neuron at the end, send a spike from S at a particular time, and that would actually work. Or do an AND like that. But again, I won't go into it. Let's do 8 and 0. Let's do the max and the min. So 8 and 0, this should be the Y neuron firing, which it does. If I do 0 and 8, then we have the N neuron firing, which is good. And then let's do ties. So if we have 3 and 3, the Y neuron should fire, which it does. And as you can see, the C neuron fired. That's the AND neuron that said, hey, A and B both spiked. And so since they both spiked, I'm breaking the ties for Y. And we can change those values, 2 and 2. So it should be the same thing, different time. Same spike. Here, 0, 0. Comes at the very last time. Okay, that works. So that's the mechanics of this network, how it works. We can take a look at the network itself. It's a fairly big one here because we got a lot of stuff going on here. Okay. But as you can see, it's got, there are max thresholds, which are in here in those green neurons. This one has a threshold of 2, right? You'll see that. That's in the blue neuron with the various delays, etc. It's pretty easy to read. Okay, and then the processor tool commands. So, let's do something more interesting. Let's do that 3 and 2. 3 and 2. Okay, so our processor tool commands here are now saying, hey, we're spiking 3 times into the Y, into CY. We are spiking 2 times into CN, that's this one, and we're spiking the S neuron once. Its threshold is 1, the value of 1, that's going to make it spike. It is interesting, these spike trains don't have to be strict. They just have to come within the maximum number of spikes. So in fact, we could change these timings. We could make this 2, 4, and 6. Make this 1 and 7. Right? The spikes are all coming in at different times, but it's going to take the count of them and compare them and do the right thing. So, probe in processor tool RISP. Right. We should see that the Y neuron is spiking. Yeah, even though these guys came in at different times. Right? You can see here, you can see the times that they came in. Okay. Let me just also remark a little on the shell script here because it's a meaty shell script. If we look at the shell script itself, number 9, all these shell scripts go through the same process, which is actually the same process as the testing scripts in the open source repo. Basically, the first thing you do is create an empty network that has the correct parameters for the processor in there. That's correct, doing the parameters. And then we create an empty network. Then we load the empty network. We create all the neurons, set their names, set their thresholds. This is all a shell script. This is creating commands for the network tool. Right? Then we create all of the edges. Then we set all of the weights and delays of the edges, right? You notice this is Bourne shell syntax doing arithmetic. Right? And then we save the network into tempNetwork.txt. So all of these commands get put on a standard output, and then that gets piped into the network tool. And then we go ahead and we create the processor tool commands, put it in there, and run it. It's a straightforward shell script. It's a nice pattern to go through. One of the reasons I like this pattern is that in case we change some network formats, it's fine because we're going to be using the network tool to create stuff. So in fact, these scripts won't go stale even if we have some minor changes to the software. Okay, that's that. 2 more videos to go.